Mr. Ernst, we're here for lesson 2.2 part A, and in this lesson we're primarily focusing on the empirical rule, 68, 95, 99.7. But before we begin, we're going to kind of get used to some of the terminology and some of the setups that we're going to have. So let's start off first with where are we and where have we been. In chapter 1, we looked at where are we overall as a group. We looked at the distributions of either a sample or a population, and we learned to describe overall how the entire population or sample is doing. We learned the shape, center spread, outliers, SOCs. In chapter 2, what we're doing is we're going within the group. We're looking at how do I compare to the others around me. You know, what's my percentile? Where's my standing? How do I compare to the average? We're starting to look at where do I stand within the group of us. Now we're inside the distribution, comparing within it. So we need to standardize in order to do that. So some things we do compare. I mean, we compare SAT scores to ACT scores. We compare AP Stats to AP Calc. We compare like districts. We compare finances, standardized test scores. There's all these different things that we compare. We need a standardized system to do it. And that's what we're going to learn in this lesson. And so first off, some of the notation that we're going to be using. And so we see right here, we have a table to kind of outline it for us. Is we have a parameter and we have a statistic. And what we're going to keep in mind is that a parameter begins with P, and so does the word population. So a parameter is a numerical characteristic of a population. We also see a statistic, which begins with S, is a numerical characteristic about a sample, which also begins with S. So there's how we're going to know which one we're dealing with. A parameter deals with everybody in the population. A sample deals with just a, statistic deals with just a sample. Now a proportion, and we have a mean. Now when we're looking at a population proportion, we're looking at parameter proportion. We don't use theta. We're going to use P for it. We use Greek letter mu for the parameter mean, the population mean, and we use the Greek letter sigma for the parameter standard deviation, the population standard deviation. Now for the statistics, we use p hat when it comes to the sample proportion, statistic proportion. We use x bar when it comes to the sample mean, the statistic mean. And we use the lowercase letter s for the sample standard deviation. Now you see these variables on the side, and this is from chapter 1, is we had two types of variables. We had quantitative and we had categorical. Now remember, when we're dealing with categorical variables, we're really looking at proportions for it. And you can think about pie charts or bar charts for that. When we deal with quantitative variables, we're looking at something kind of like the mean. So that's really what we have here, and I'll even cross this out like we had before so you can see there's the setups that you should have on your notes for it. So p hat for sample proportion, x bar for sample mean. If you have a p, it's for the population proportion. If you have a mu, it's a population mean. And then sigma for population standard deviation, s for sample standard deviation. So now let's move on into normal distributions for this. And a normal distribution is an important type of density curve. And do remember that density curves, they should have an area of 1 underneath them. So let's keep that in mind. So a normal curve, which we describe as normal distributions. A normal curve is symmetric, single peak, and bell-shaped. Really important characteristic. Now we define them, we describe them, and want to keep this in mind by looking at its mean and its standard deviation. So let's go back to chapter 1. We were looking at the whole population, and we used SOCs to describe the whole population. We used shape, outlier, center, spread. Well, it's a normal distribution, so there are no outliers. So let's look at just shape, center, spread. And it looks like how do we define that? Well, it's simple. It's a normal distribution curve. Well, there's your shape. It's normal. What's the center? Well, the center looks like it's the mean, mu. So my center, parentheses, is mu. Well, what's its spread? Well, its spread is the variation. We have our standard deviation of sigma. So let's do comma sigma. And so this is our notation when it comes to shape, center, spread for a normal distribution. So we're still addressing those same things from chapter 1, shape, center, spread. No outliers because it's normal. So we look at this example down here, and I want to kind of discuss on these are two different types of normal distributions. And look at them. One thing to keep in mind is that your mean is the center of the distribution for it. And you can see we have outlined one standard deviation away from the mean. what I'm going to do is I'm going to put context here so we can understand, even though they're both normal distributions, there's interesting characteristics about them. I'm going to create a horizontal axis here, and I'm going to label it. And let's label it that this is the number of points per player, and we'll say on a basketball team. Okay, so we have context on it. And if I'm looking at that horizontal axis, we'll make it look a little bit nicer, is if we look at that horizontal axis, I can put some numbers on there to make it a little bit easier. And so what I'm going to have is, we'll say the average for this team, let's say the average amount of points for them is, per player, let's say it's 12. And I'm going to tell you the standard deviation is 6. And so that means that with 18, with one standard deviation for points would be from 12 to 18. And this is just to put context to it. I mean, the other one's a normal distribution as well, but look at that one. It's pushed in more. So let me take this same scale. Let me take this right here, and I'm going to duplicate it. I'm going to match up my centers. And so notice on here, when I'm looking at it, is the standard deviation smaller. If I were to come down and hit right here, I mean, one standard deviation in this case, maybe it's 4. I mean, it looks like it splits it in half on that, which that means their spread is smaller. So if you think about this in context to the basketball team, the team on the left, they have a wide variety of skills on their team. And there's a middle of 12, just like the same on the other one, but they got some good players all the way on the other side on. You got some poor players on the other side on. They have a wider spread. The one on the right, their players are more consistent with each other. For the most part, a lot of that is actually a tighter amount. They don't have as much spread for it. Just something to keep in mind, that the normal distributions, they follow a certain rule. But you can see there's 2 different types here, and the spread there is interesting compared to the other. It's smaller spread. Now this is a very special type of density curve we talked about. What I want to know, and this is blue, it's not on your notes, but I want to make sure you understand right here, is that the point of inflections are where the one standard deviation away from the mean, both positive and negative, occur on a normal distribution. So remember, points of inflection are where they change from opening up to opening down, or from opening down to up. So if I trace this out and I think about it, I'm opening down, I'm opening down, I'm opening down. Maybe around this point right here is where I start to see, if this were to be a curve, it's now starting to open up. And the same on the other side. It would be, this is a curve and it's starting to open up, and it'd be the same thing on the top. Go to red, this one's opening down. So these locations right here and here, and this is an approximation, those would be within one standard deviation mean. That would be the location of one standard deviation to the left and one standard deviation to the right. And it's just an important trait to keep in mind, that plus or minus one standard deviation from the mean on a normal distribution occurs at the point of inflection. So let's keep going. Also, a normal distribution, not a parabola. It is not a parabola. It is not U-shaped. A couple reasons why. The one of your notes says the area under the curve is one reason why as well. It's not just the shape. You can see it visually in there. I created this in Desmos, so took a picture of it. You can see they're not the same, but it's also the area on it. Remember, a quadratic area changes based off of where that graph is on the XY axis. But for a normal distribution, its area follows the area of a density curve, which means the area under that whole normal distribution curve is 1. That's a really important trait to keep in mind. The other reason why you can see that this is normal is because normal distributions, the ends kind of have an asymptote behavior with the x-axis on it. It's not like it's going to go across the x-axis, but the parabola will cross the x-axis on it. That's how that works. The normal distribution is going to keep on fanning out further and further, and just keep approaching it like an asymptote. So keep that in mind for it. Something that we do is students will see this, and a problem will go, okay, this is a normal distribution, right? Yes, no, and the answer is no. Like it might be a parabola, but you don't know unless the area under it's 1. And you don't know unless it follows a standard deviation rule. And there's actually another rule when it comes to standard deviations we're going to look at in this video. But just because, bottom line I guess is, just because you see an upside down curved graph does not mean it's a normal distribution. it has to follow certain criteria. Plus or minus 1 standard deviation is the points of inflection. The area under it has to be 1 like a density curve. Another rule that it follows is the empirical rule, which is what we're covering in this lesson for it. So before we start the empirical rule, let's just kind of look at some of the definitions, and I'll just go here and talk about it. When you're looking at it, a normal distribution is a type of density curve. Again, don't just kind of skim past these definitions. These definitions make up your multiple choice questions a lot, these properties on them. Remember, density curve, it has an area of 1 underneath it. It is defined by 2 numbers, the mean, center, the standard deviation, spread, and normal, shape. So when we describe it, we still describe it with the shape, the center, and the spread. And that's what this part right here talks about. You are describing the shape, it's normal. Parentheses, the center, it's mu. Comma, the spread, sigma. We define it using that notation for it. And that second bullet point, I didn't read it, but it's what we talked about before. The points of inflection, the change in curvature, is within 1 standard deviation of the mean. Now, those are properties of normal distributions. When we look at this, one thing that's going to happen is right here, statistical inference. That's going to be a huge thing in this this course as we progress through the year. It's really like the last quarter half, maybe even close to the last semester of content that we deal with is with inference for it. So here is the empirical rule. This is another property that it's with normal distributions. If you have the center, and within 1 standard deviation to the left and to the right of the center is approximately 68% of the observations. 2 standard deviations from the right and center in both directions is going to be approximately 95% of the observations. 3 standard deviations from the center was approximately 99.7% of the observations. So that's what this picture really shows us. It breaks down the empirical rule by going 1 standard deviation left and to the right, 1 standard deviation left and the right, and from there. So 68 within 1, 95 within 2, 99.7 within 3. 68, 95, 99.7. That's an empirical rule, something that we really need to look at. And this is a visual to show you graphically. If this is my center, and I go to the right one, and I go to the left one, we can see that that is 68% of the information. If I go to the right 2 and the left 2, you can see that is 95% of the information. And we can break down that empirical rule even more on it. We can see what's within 1 to the left, 1 to the right, but what if I decide to kind of just break it apart even more and find out how much is here, or here, or here, or here, or here, and so on. And that's what we're going to do. Your next part of the notes has this problem that deals with the mean SAT score. On the top right of your paper, there is a graph that looks like this. And we can break this down. And we're going to break down the empirical rule. And we're going to, I'll cut it in half right here. And we're going to realize it's symmetrical. That's a key. And we're going to break down to 68. Now, 68% of the information lies within 1 standard deviation. So from here to here, within those blue lines is 68% of the observations. Well, if I want to know how much percent of the observations lie within the 0 standard deviations to 1 standard deviation. So really, how much lies within here? Or how much lies within here? Well, if 68's in both combined and it's symmetrical, we're going to divide by 2. And so this is 34%. And this is 34% of the information. Next, we have 95. And I'm going to slide this 68% down. 95% of the information lies within 2 standard deviations of the mean. So here's 95%. So what I want to do is I want to find out how much lies from 1 to 2. So what percent of the information lies in that little area right there? Or how much percent of the information lies within this little area here? Well, if 95 is that entire thing, and that middle blue part is 68, I'm going to subtract those. And I'm going to see total 27% of the information lies in both of those combined. And it's symmetrical. So I'm going to divide those by 2. And I'm going to get 13.5%. And so there's that one. I'm going to erase the 68%. And I'm going to slide down the 95, kind of like what I did before. And now we're looking at the last part. Let's go purple. 99.7. 99.7 lies from -3 to +3 standard deviation. So 3 to the right, 3 to the left of the mean, that is 99.7. That's a lot. And so 99.7 lies here, percent of the information. So again, I know 95 is in that green area. I can subtract those two and get 4.7. Now 4.7 is both of those combined, and it's symmetrical, so we're going to divide by 2. So I have 2.35% here, and I have 2.35% here. And we're not quite done. Yes, it's the 68, 95, 99.7 rule, but there's another part of that rule, and it's the density curve property, that underneath that curve in general is 100% of the information. The area under it's 1. So 100% of the observations is under that entire curve. So how much lies outside 3 in both directions? That's the other part we're going to figure out. And so if 99.7 is from the purple to purple, and the entire thing contains 100%, then that means, and we'll go red for this one, that means that 0.3% lies in both this area and this area, all the way to the right. Not just from -3 to 4, but all the way. From +3 and to 4, all the way. It's the rest of it. In those tails is 0.3% combined. So I'm going to divide by 2. And so that gives me 0.15% in each of those tails extending forever. So man, if you are 3 standard deviations away from the mean, or 3.5 standard deviations from the mean, or 3.6, 3.7, that's a small percent on there. Just think about that. And so we go through. Here is the picture that I just drew. Now, personally, I would pause the video right now, and I would look at my formula sheet where we have the table outline on the attached part. The chapter 1 notes, that area, that box. You have a chapter 2. The empirical rule would be a good thing to kind of slide in there on it, just to kind of get used to it. So I would pause the video and take a look and kind of maybe copy that down to make sure you understand the breakdown in each from 0 to 1, 1 to 2, 2 to 3, 3 beyond. And same thing on the negative side. We're going to apply it in this one. So I'm going to magically make all this information appear. And there's our breakdown. The 34, 13.5, 2.35, 0.15% magically appeared. That's perfect. Now, some things to keep in mind, this is going to be hit pretty hard in the next video, is do I really need to sketch and label a graph of a normal distribution curve? Yes. Yes, you do. But I did it in the previous problem. You still have to do it again. But if I did it before, do I really need to do it again? Yes. Yes, you really do. Now, I'm using one of these for the entire thing. And as we go further, yes, there are 5 questions, and you would have to sketch 5 curves and label them and show the shading for them. So as you see in the next video, you will have to do that every single time. And yes, every single time you need to address the shape, the center, and the spread. Every single time. And I am doing that. I'm going to mark it here. And look at the prompt. It says you have a mean math score on the SAT of 500. Well, for a normal distribution, that goes in the center. Look at that. I defined the center. Check. I defined that it's a normal distribution. Look at that curve. That's a normal distribution curve. I defined the shape for it. Now I need to define the standard deviation. It's 90. So I'm going to go 90 to the right. There's 590. I defined the standard deviation. Boom. So you see how we are defining shape, center, spread constantly, which is why you do need to do a graph each time. I'll continue and I'll stop saying that, but it's that important. So I'm going to subtract 90, and I'm going to say this is 410. I'm going to keep doing that across the entire bottom. I'm going to add 90, and I'm going to get 680. I'm going to get 770, and I'm going to even do 4, and I'll do this as 860. I'm going to subtract and go the other direction. So this is 320, this is 230, and this is 140. And so we have this. And this is kind of just to show. I have it labeled. Now I can answer these questions. What percent of students' scores will be less than 500? So I would sketch my curve. I would graph it. I would label it. And I'm actually even going to shade it. And so less than 500 would be here and all the way. So I'm going to shade it. So I want to know what percent lies within there. Now I could add up 0.15, 2.35, 13.5, and so on. But really, that's half the normal distribution curve. That is 50 It cut it in half. So boom, done. Next one. What percent of students' scores will be less than 410? So again, I'm going to highlight. So here's 410. Boom, and I would shade after I graphed it. There we go. Well, in this case, I'm going to add. I'm going to take my 0.15. I'm going to add my 2.35. And I'm going to add the 13.5 on it. And when I add those, I am going to get 16%. So 16% have less than 410 as their score. What percent of students, let's erase, boom. What percent of students have a score greater than 680? So let's see, 680 is right here. I'm going to go to the right for that for my shading. So that would be 2.35 plus 0.15. So that is 2.5%. I took my 2.35 and I added the 0.15, 2.5%. And so this is where the empirical rule allows us, as long as we are within the standard deviations, we can add up those numbers. So 320 to 590. Now this one, if I were to go from 320 right here to 590, which is right here, now you could add up the numbers that we see. I could take 34 plus 13.5, and I can get my answer. Now me, I take 68 and I add 13.5. And I know that's the same as 34 plus 34, but just bear with me. I could see there is some symmetry from one standard deviation to the left and one standard deviation to the right. So that's 68 and then the 13.5 on it. And that's going to give you your answer. So you can do all of them together, or you can do the 68 plus 13.5, and you're going to get 81.5 for your answer on it. So 81.5%. I could do the 13.5 plus 34 plus 34, or just do the plus 68. So there we are. This is kind of just practice of the empirical rule. Now what I'm going to do next is I'm going to have a little fun. What percent of students lie less than 545? So this one's a little unique. Right, we'll do purple. Right here is 545. That's half a standard deviation away from the mean. Not in this empirical rule. Very interesting. This one's a little bit different. Half a standard deviation from the mean. And so what a lot of students want to do is they want to go, hey, I can take that one standard deviation, that 90, and I can cut it in half because of symmetry. But look at the picture. If you were to do that, you're telling me that this area right here for this object has the same area as this object. And you can see visually they don't. One's taller than the other. One reaches further up than the other. It contains more. It's getting smaller on the outside. They don't have the same area. Symmetry doesn't work here. So what do we do when we don't have a standard deviation that is 1, 2, 3, or -1, -2, -3 away from the mean? What if it's not a nice standard deviation? What if it's 0.5 standard deviations? I can't use the empirical rule. And that's where we're going in this. And the next video goes on that. It discusses on how do we address a 0.5 standard deviation, or a 0.237 standard deviation, or a 3.21 standard deviations. How do we address all those little z-scores in between them? And that's where this part, and we're not going to go over this part of the notes, but I want to show you that's where this leads into. The empirical rule is great when it comes into what we're doing when along the lines of nice 1 standard deviations, 2, 3 standard deviations away from the mean. When they're in between them, we need z-scores. And we're going to use that next. Now, hey, if you stayed and watched this video for the entire 24 minutes so far, then good news, you get to go over one of the homework problems. This is a really nice homework problem. It discusses everything we did before, and I just want to talk about it for a minute because I don't want you just to write an answer down and not understand the concept. We're told this is a normal distribution graph, and we want asked to find the mean, median, and the standard deviation. Now, what I'm going to do is I'm going to kind of just come right down from the center, and I'm going to tell you the mean and the median is a score of 150. So 150 is my mean and median. So now what I'm going to do is I'm going to go further and find the standard deviation. This is why I'm putting this in the video. If this were a multiple choice question, one of the choices would be 50 because they labeled by 50s in the bottom, and that's wrong. It's not a 50. That just because they label the axis there doesn't mean that it is guaranteed to be the labels of the standard deviation. And remember, standard deviation is within one standard deviation to the left and the right of the mean is the points of inflection. So you could approximate it by looking at where you think those points of inflection occur on it. And that's a really hard thing to do, but it could help you on a multiple choice problem. Now, the way we're going to do this is we're going to realize when it comes to the empirical rule, come up to this part of the picture, is we can see 1, 2, 3, 4, 5, 6, 7, 8 sections. So there's 8 sections on that. But if I look at this one right here, and this is where I kind of zoom in, is that's not quite a symmetrical graph with the axes. So you can notice that it's not quite fair. If you look at it, you're going 250 in one direction, you're going 300 in the other direction. So it's not there. So I'm going to say like this, the left side of that graph is actually smaller than the right side of the graph when it comes to lengthwise. So I'm going to treat like we're going to have -3 standard deviations over here, and we have 4 standard deviations over here. So that entire thing, I'm going to approximate by saying there's 7 standard deviations from the left to the right of that picture. And that's going to allow me to take and figure the whole thing out. So from here to here, I'm saying is 7 standard deviations. Well, numerically, from -100 to 450, that is a total distance from here to here of 550 in there. I'm going to take that number, 550, and I'm going to divide it by my 7. And when I do that, I'm going to get it close to about 78.6. So each standard deviation is approximately 78.6. And you could say, hey, maybe each standard deviation is approximately 80. I'm going to say it's 78.6 because, you know what? I like perfection. And so we're going to do that. So that is this one. The main idea, and I mean, if you didn't get 78.6, if you got 80, good for you. If you didn't divide by 7 and you divided by 6, you still have the idea down, and that's okay. The main point of this problem was so you did not write down 50 there. That was the main thing we wanted to get. And that is the end of lesson 2.2a. 2.2b, like I said, we're going to start looking at those in-between z-scores.